Hello and welcome to my presentation on my final year project. I'm Austine, and under the guidance of my supervisor, Prof. DECENTRALIZED, I have completed my 2 semesters research project on the topic of collaborative decentralized machine learning for Internet of Things. In this video, I'll be giving a quick introduction on my project. Let's first begin with the motivation behind this area of research. In recent years, there have been an increasing number of security breach incidents. Recent incidents of security breaches include massive organizations like Microsoft, Zoom, and Facebook. These incidents are often costly to rectify and result in large-scale leakages of private and sensitive personal data. In today's day and age, with data considered as the new oil, the consequences of a large-scale data leak is immeasurable. In fact, as of 2019, cyber attacks are considered among the top 5 risks to global stability. Due to this, there has been an increasing focus on privacy preservation measures worldwide. Governments worldwide are seen enacting regulations and bills regarding the protection of data in order to actively combat the risks of cyber attacks. For example, the General Data Protection Regulation in Europe and California Consumer Privacy Act in California has seen the implementation of new stipulations for collecting and using consumers' personal data, ultimately granting consumers better control of their own data. A novel approach to machine learning, federated learning, was introduced in recent years. Federated learning is a collaborative machine learning technique that trains a model across decentralized edge devices while keeping all training data on device. Each edge device downloads the current global model, conducts training with local data, then communicates the model updates for aggregation with other devices to improve the global model. With a federated learning approach, data remains on device and is not stored by a central organization, minimizing the risk of data leakage from a central organization that stores the raw sensitive data. It also allows for personalized model updates according to each user's preferences and usage. However, existing implementations are often limited by 2 challenges. Firstly, federated learning is communication intensive compared to traditional approaches, as it involves multiple iterative communication of local model updates. Furthermore, there is a heavy reliance on a central server to conduct model update aggregation before updating the final global model. These limitations thus highlight the basis for the scope of this project. First, we will implement, evaluate, and tune the hyperparameters in our federated learning setup. We will also be exploring and comparing different gradient compression schemes, mainly focusing on the communication cost reduction against model accuracy. The system design of my approach is thus as follows. For hyperparameter evaluation, an existing federated learning framework will first be implemented. The effects of traditional and federated model hyperparameters on overall model accuracy will then be analyzed for both IID and non-IID environments. In order to do this, experiments were conducted on the MNIST handwritten digit recognizer task with a convolutional neural network model. The MNIST dataset is first artificially partitioned into different shards in order to simulate the edge devices in a federated learning setup. For the IID setup, the dataset is randomly sampled and partitioned, while the dataset is selectively partitioned according to the training labels for the non-IID setup. This way, the experiments would be conducted in both an IID and simulated non-IID setup. This is significant as federated learning is often conducted with non-IID data, since each device's data is largely skewed to that particular user. Next, we will implement multiple gradient compression schemes in order to evaluate the trade-off between overall model accuracy and communication overhead. For this, we will evaluate 3 gradient compression schemes in particular: deep gradient compression, top K, and random K gradient compression schemes. Using the framework from the first part of the project, we then construct a distributed learning setup using PyTorch distributed for multi-process coordination and communication. Each process thus simulates an edge device in the federated learning setup, and the communication between each process is analyzed against the overall model accuracy. With that, I have come to the end of this quick introduction to my final year project. Thank you for listening.